We're now at week 2 of the course Discrete Mathematics, and the central feature of this week is the study of recurrence relations. So in the notes there's section 2.1 and section 2.2. These are both fairly introductory to the subject, and I'm not going to speak as such about these sections. 2.1 includes the so-called Collatz conjecture, mention of the so-called Collatz function, and this shows you that the notion of a recursive function, recursively defined function, can be quite a deep problem. So you can look at that, and there's also a problem on sheet 2 about this. And there are some simple examples as well. Section 2.2 is denoted mainly to the Fibonacci numbers. And I talked about these in the introductory video, part 1. So if you haven't seen that, please look at that, unless you know everything about the Fibonacci numbers already, which may be the case. And at the end of section 2.2, there are some formal definitions of a recurrence relation. So I'll mention, I won't go through the definitions formally in this video, but I'll mention the definitions by means of examples. But I recommend that you do look first of all at these definitions which come at the end of section 2.2. So that's important. I don't know why they were put there and not in the next section. Anyway, so this video really addresses section 2.3. And I want to give examples of the sort of recurrence relations which we'll be dealing with in this module and that you'll have to solve. So typically these are what are called quadratic recurrence relations, with often with constant coefficients, mostly with constant coefficients, but typically non-homogeneous. There'll be an extra function. It's all analogous to the theory of differential equations. So let me start with the equations defining the Fibonacci numbers, because in some sense this is a sort of prototype quadratic recurrence relation. Although it's homogeneous, there's no extra term. So remember, what is the equation defining the Fibonacci numbers? So it's Fn. The nth Fibonacci number is called capital Fn. And this is simply defined to be Fn minus 1 plus Fn minus 2. And we have to solve that. Now, there will be many solutions unless we apply initial conditions. And the point here is that Fn is a sequence, so formally we should maybe put it in round brackets, and we normally think of it as starting when n is 0. So if you like, it's a sequence, strictly speaking, n goes from 0 to infinity, all that sort of analysis notation, which we won't on the whole adopt. But the important thing is we do normally assign a value to f0, and it's quite easy to remember what f0 is. It's equal to 0, whereas f1 is defined to equal 1. And we need those initial values in order to specify uniquely the Fibonacci numbers. Then, for example, that will tell us using the recurrence relation that f2 is equal to 1 as well. And I did a table of these in the introduction. For example, f5, the one I remember is that f5 is equal to 5, fn is equal to n in that particular case, and so on. So these are the Fibonacci numbers, and we can also write the recurrence relation as fn minus fn minus 1 minus fn minus 2 is equal to 0. And you can sort of think about that as being written in the form, it's a bit like sort of starting with the sequence or the term fn minus 2, or in some sense the sequence shifted minus 2, and we're applying a sort of operator s for shift, and minus s squared minus s minus the identity really applied to fn minus 2, where s shifts the index So here by 1, here by 2. So in some sense, just formally, you can think of the recurrence relation as written like that. And that explains why this polynomial equation here is rather important. We can just write it as x squared minus x minus 1. So somehow the Fibonacci numbers are very much related to this quadratic equation. And this quadratic equation, if we look at the roots of this equation, when we set this equal to 0, this will tell us what is x. X is equal to 1 plus or minus 1 plus 4, that's 5, over root 2. So x over 2. So x is equal to 1 plus or minus root 5 over 2. And in fact, there's a formula for the Fibonacci numbers. It is that Fn is equal to 1 over root 5 times phi to the power n minus psi to the power n, where phi is the root with the plus sign and psi is the root with the minus sign. So phi, should have really written this with phi and psi, but phi is equal to 1 plus root 5 over 2. It's the so-called golden ratio, and psi is 1 minus root 5 over 2. That's a negative number. Okay, so that's the formula for the Fibonacci numbers, and we'll explain why that you can check that formula satisfies the initial conditions and the equation. But I'll explain through the general theory or the general approach to solving these recurrence relations why that sort of formula works. Okay, so let me actually start with a simpler relation. I mean, you might think this is the simplest imaginable one involving 2, 3 successive terms, but actually you get these irrational numbers, so in that sense it's not so simple. Let me give you a simpler relation, which I'll use by way of an example. So I'm going to start again really. I'm going to give you this recurrence relation. So here's the sort of solved exercise, worked example. What does one call it? Solved example. Namely, I'm going to take the recurrence relation AN, call it A now. Our sequence is typically called AN, not FN. F stands for Fibonacci. A is more general. AN is equal to 3 AN minus 1 minus 2 AN minus 2 plus 1. Now, this is sort of, if I didn't have the plus 1, it's the same sort of form as the equation for the Fibonacci numbers, except that I've changed the coefficients from being 1 and 1 to being 1 and minus 2. But I've added an extra term here, and this extra term here makes the equation, the recurrence relation, I use capital RR for the recurrence relation, what's called non-homogeneous. So lots of abbreviations here. Let's write it in full. Non-homogeneous, which later on I just call NH. Non-homogeneous. The Fibonacci relation is homogeneous because there's no extra term, and this extra term could be a function of n. The fact that these coefficients are constants, they could be functions of n. If they're functions of n, this is an example of what's called a linear recurrence relation. But because they're actually constant, this is a recurrence relation with constant coefficient. So here's another recurrence relation which crops up actually in section 2.5, I think. dn, which stands for the number of derangements, which are special types of permutations. This is actually equal to n minus 1 times dn minus 1 plus n minus 1 times dn minus 2. That's a relation Actually, the initial values, I think, in that case, at D0 is 1 and D1 is equal to 0. It's sort of the opposite of the Fibonacci numbers. This defines the so-called sequence of derangements, the number of derangements. I could have taken the n plus n minus 1 as a common factor, but I've written it like this to emphasize that we have a function of n times dn minus 1 and another function of n times dn minus 2. So this is an example of a recurrence relation which is linear. And it's homogeneous in this case because there's no extra term, so it's actually homogeneous. It's like the one above, it's second order because it involves expressing the first term in terms of two successive ones. So that's another example of a homogeneous relation, but it's not of the sort I want to consider today because it doesn't have constant coefficients. So let's put this in a box, not to confuse it with what I was saying before. So let's go back to the solved example. I haven't quite finished writing this out because I need to give you I need to specify initial values. So I think this time I'll say squeeze it in here. So with actually A0 equal to 0 and A1 equal to 0. Because this is non-homogeneous, that setting the first two terms equal to 0 will not force all the terms to be 0. It would if there were no extra term there, but since there's a plus 1, we'll see that the solution is not completely 0. Okay, so that is our problem. We need to solve this recurrence relation with these initial conditions. Okay, so let's make a start. Let me show you how to do that. So basically what you do is you look for solutions. You write down this quadratic equation, which I mentioned for the Fibonacci, the same method as we used for the Fibonacci numbers. So the associated quadratic equation, let's say the associated, in general it would be a polynomial if we have further terms. The associated polynomial one says, for tackling recurrence relations with constant coefficients, the associated polynomial is well, remember you really have to put everything on the left-hand side. So it will be, if we do that, we'll have an minus 3 plus 2. So it will be x squared minus 3x plus 2. That's the associated polynomial. If we want to make it an equation, I'll put equal to 0. And what are the roots of that equation? The roots are, first of all, we have to factorize it. Well, I've made this very easy. You see, it's actually x minus 1 times x minus 2. That's why I'm telling you this is going to be much easier to solve than the Fibonacci number relation. So the roots are plus 1 and plus 2. They're distinct and they're real, which makes this problem quite easy. And what are the roots telling you? So each root, say lambda, if the root is lambda, this gives, I think I use lambda as a variable actually in the lecture notes. Here I'm using x, but it doesn't matter. Each root lambda gives a solution to the homogeneous equation. I'll explain that in a moment. Each root gives a solution to the homogeneous equation of the form an is equal to lambda to the n. Now the homogeneous equation is not the original equation, but it's the original equation in which we've removed the extra term. So what I'm saying is that if you take lambda to be 1 or lambda to be 2, and you set an equal to 1 to the power n or 2 to the power n, you'll solve this equation. Okay, So in particular, that means in our case, so the general solution to the homogeneous equation well, we've actually found two possible solutions, 1 to the power n, which is just 1, irrespective of n, and 2 to the power n. And since this is a linear setup, and we're talking about homogeneous equations for the moment, I can take any linear combination of those solutions and get a solution. So in other words, I can take any constant a times 1 to the power n, which of course is 1, plus any constant b times 2 to the power n. So that is, of course, the same thing as a plus b times 2 to the power n. Remember, I'm using asterisk at times to represent multiplication. Okay, let me just summarize on a separate sheet. So what's going on here is that we started with an equation which was an is equal to 3n minus 1 minus 2 an minus 2 plus 1. That's the so-called non-homogeneous equation. And for the moment, we're really forgetting about this extra term, and we're considering the, I'll write it slightly differently, I'll put the other stuff on the left, minus 3n an minus 1 plus 2 an minus 2 equal to 0. That's the associated homogeneous equation. Okay, and what I'm telling you is that the homogeneous equation has general solution. So the general solution, any solution of the homogeneous equation, the second one, has to have the form constant a plus b times 2 to the n, where capital A and capital B are arbitrary constants. They can be anything for the moment. Because I haven't mentioned here the initial conditions, we haven't even got back to our original equation, which is this one. But we made some progress. Okay, now what we have to do is we have to go back to the original equation. We want to find one solution to the original equation with the 1. Okay, now here there's an extra complication which I've put in on purpose. Typically, if you have a constant term, and it's the next section 2.4 which will explain to you more in detail how to deal with these extra terms, but if you just have a constant here, you would expect to be able to find a solution of the recurrence relation by just taking a different, possibly different constant. But that won't work here because any constant already solves the homogeneous equation. So to find a particular solution, to the non-homogeneous equation, we're going to sort of guess, if you like. I mean, it's not really a guess because I know what I'm doing, but we attempt to find a solution. You would normally try a constant, since this is a constant, but that's before we saw that the constant solves the homogeneous equation, so there's no point in me taking a constant. So what you do is you multiply what you would have guessed by n. So we guess an is equal to some other constant. It's a bit dangerous, but I normally use alpha for this, as long as you realise alpha is not n. Alpha a constant. A constant. So that's what I would have guessed. I'm getting confused with my A's and B's. Alpha is a constant. That's what I would have guessed, but I need to put an n in here, because without the n, this would not solve the non-homogeneous equation, because it's already a solution of the homogeneous equation. So we guess an is equal to alpha times n, and we substitute that in. So substituting that in to the original non-homogeneous equation, what do we get? We get alpha n is equal to 3 times alpha n minus 1, because an minus 1 would be alpha n minus 1, minus 2 alpha n minus 2 plus 1. That's what we get. We need to just solve this for alpha. Well, the coefficients, because we've got an equation like this has to be true for all n. And so the coefficients of n, if you look at the coefficients of n, you'll have alpha is equal to 3 alpha minus 2 alpha. Well, that's always going to be true. That's really why we had to multiply by n. So that's already true. And then we look at the constant terms. We have minus 3 alpha plus 4 alpha plus 1. So this single equation, because this is true for all values of n, allows us to separate out the coefficients of n and the constant coefficients. And the second equation, the first one's automatically valid. The second one tells us, what does it tell us? That alpha is minus 1, I guess. Alpha is equal to minus 1, because we get alpha plus 1 is 0. Okay, so we've now got a particular solution, namely minus n. Okay, minus n will work. We can just check that. So let's just check minus n. Let's go right back to the beginning. Let's just check. Is it true that minus n is equal to minus 3 into n minus 1 minus 2 into n minus 2 plus 1? Well, it's the calculation we've just done, so it should work unless we made a mistake. As you stare at this, you'll see that this is true. 3 plus 4 minus 3. So there's no minus here. I made a mistake. It's my mistake. Minus, oh no, it's not my mistake, because there was a minus 1 here, so there was a minus there, but then this becomes plus because of the minus. So that is correct. We get 3 minus 4 plus 1 is 0. So that is correct. Once I've corrected my signs. So we have a particular solution. And so because we've got this particular solution, we can say that the general solution of the non-homogeneous equation, NH, is equal to our general solution of the homogeneous equation. So we're still involving two arbitrary constants. And then we add on our particular solution, which is minus n. Okay, so let's just say this is the general sort of setup that happens. So here we have the general solution of the homogeneous equation. And here we have one particular, there will be others because I can just add in any things from here. I have one particular solution, just one solution. It's often called one particular solution of the non-homogeneous equation. Okay, now we've almost finished our example. We've just got to satisfy the initial conditions. Okay, so let me do that now. Let's leave that visible. So we now, this is the, let's just go back and see what we've done. The first step was to solve the homogeneous equation. Okay, so the work for that was on the previous page. And then the second step was to find a particular solution. And now if we've got, could stop there if we weren't given initial conditions, but because we were given initial conditions, we have to satisfy the initial conditions. So we need to determine, the third step then is to find, determine our arbitrary constants that we still have in here, A and B, so as to satisfy the initial conditions, which in this case, well, let's just say initial conditions, initial values. What were the initial values? Well, the initial values were, writing it backwards, they were A0 is equal to 0, but what is A0? Well, A0, I said this is the general solution of NH. What I meant, therefore, is to say that AN is equal to all this stuff. That's what I'm saying. So A0 is equal to A plus B times 2 to the 0. That's just B minus 0. And A1 we also want to be 0, but A1's a bit more complicated. So A1 is equal to, oh no, I should remove that bit too quickly, didn't I? A1 is equal to A plus 2B, B times 2, which is 2B, and then we do have a minus 1. Okay, I'm looking here, when n is 1. Okay, so we just have to solve those two equations fairly easy, I hope. So the first one tells us that A is minus B, or B is minus A. And since we know that B is minus A, we now have A minus 2A, that's minus A, minus 1. So that tells us that A is minus 1. I can get rid of that finally. And so we have the third step then tells us that, so the final solution of our recurrence relation with initial values is AN is equal to A minus 1 plus B, that's plus 1 times 2 to the n, minus our particular solution, which is n. Okay, again we can check, of course, this must satisfy the initial conditions. A0 is equal to 0 and A1 is equal to minus 1 plus 2 minus 1, so that's correct. So that is the final solution. And that is basically the method for solving this type of recurrence relation. It can be complicated by the fact that if you have more complicated extra terms, here our extra term was just a constant minus 1, or plus 1, plus 1. In general, you might have a more complicated function of n, and you have to know what to guess as your particular solution. And that will be the subject of the next talk and section in the notes. Thank you.